So I think we're probably ready to start. I don't know who's chairing.
Sure.
Chen Chang, do you want to chair?
Sure, I can. Yeah, so we're very happy to have Yanpeng Li to talk on tropical Poisson-Lie theory in global Poisson. Please, Yanpeng.
Thanks for the invitation and the introduction. Yes, there's one thing I want to say that Anton Jeremy is giving a lecture roughly on the same topic. So I hope my talk today will be a good extension of their lectures. The second thing I want to say is that most part of the talk are like in my PhD thesis, which makes me feel I'm giving a second PhD like a defense. I hope it will be a success. So the title of the talk is kind of ambitious. Oh, sorry. Yeah, the title of the talk is kind of ambitious. Actually, we are at a very early stage of building this whole theory. So in our dream, we hope this theory to find some new connections between integral systems, Poisson geometry, and the representation theory. So now let's start by recalling what is Poisson-Lie groups. What are Poisson-Lie groups? By a Poisson-Lie group, it is a Lie group together with a Poisson bivector, such that the multiplication of the group is a Poisson map. So the easiest example is just the group G with 0 Poisson bivector. And since if you have a Poisson-Lie group, you can get a Lie bialgebra, which is a Lie algebra of G and together with some structure getting from the Poisson bracket, which gives you a Lie bracket on the dual space of the Lie algebra. And also the two Lie algebra should satisfy some compatibility condition. And thus you can integrate the dual Lie algebra to get a dual Poisson-Lie group. There's a saying like a Poisson-Lie group is a semi-classical limit of the quantum group, if you are familiar with quantum groups. So there are more examples. The first one is K0, where K is compact. 0 is just a 0 Poisson bracket, but the dual is non-trivial. Since the Poisson here is trivial, thus on K star, the group structure is trivial, it's just abelian. Since K has a non-trivial group structure, which gives a non-trivial Poisson structure on K star, which here is just the KKS bracket or the linear Poisson structure here. And the second one is coming from given by the R matrix. And we call this one the standard Poisson structure. Later, I will give another description, or which is one of our motivation of this whole project. This Poisson structure has a compact real form, and if you take the dual of this compact real form, you get another Poisson-Lie group. As a Lie group, it is a subgroup of G given by the Iwasawa decomposition of K. And this guy will play is our main player of today's talk. So next, let me explain our motivation. So the first thing is that the double brass cell GUV is a union of symplectic leaves, and this guy has more structure, which is like a cluster structure. And Kogan and Levinsky showed that in such chart or such special coordinates, the Poisson bracket has a special form, which is the so-called log canonical. Means that if you take the bracket of the chart we choose, it only has one term, one quadratic term, pi ij times ai times ag. It's called log canonical because if you do some change of variables, you get a constant bracket. So And this chart, as I said, can in the original paper of Kogan and Zelevinsky, they are using the twisted cluster chart. And later, in the work of Gachmann, Shapiro, and Weinstein, they show the twist map is a anti-Poisson, so that which means you can use cluster chart as well. It is also log canonical. Then the natural question is, what about J star? What about K star? For J star, I think there are already a lot of works trying to build log canonical brackets. For example, for Gromov and Shen. And also recently, Gachmann, they constructed some like a generalized cluster, which is log canonical. But their charts doesn't apply to K star easily, because from J star to K star, you need to apply some involution, and to get a log canonical chart for K star, the chart on J star should have like some compatibility with the involution you choose. But this is not the case. And in my talk today, I will try to solve this problem or in some other form. So any question about this part? If not, let's move to the first part of my talk, Poisson-Lie duality and Langlands duality. So here, let me start with the example of the partial tropicalization of SU2 star. Recall that the dual Poisson-Lie group SU2 star is identified with a subgroup of SL2C. So here A is real, B is complex. So it's a real group of 3 dimensions. And the Poisson bracket for this guy is determined by these 3 formula. So by looking at these formulas, the bracket between AB is log canonical because it only contains the term AB. The bracket between A and B bar is log canonical, but the one between B and B bar is not. So what should we do? We want to introduce a parameter T in the changing of variable. Before we just take log, and now we take a scaled log, because B is complex and we are considering SU2 as a real group. So there will be angles. And now using this new chart, new coordinate, one can write down the Poisson bracket. So here we're caring about the scaled one. So we get this bracket, we get this bivector. Okay. Now let's look at this bivector more carefully. So the first term is already a constant, but the second is not. The good thing is that it has a parameter T inside, which means we can do something. So now if we take T to infinity, this term will vanish on some places. And this place is actually a cone, because so here, I mean, this cone is just given by how to say, psi A minus psi B. We need this term to be less than 0. And this term, we want psi A plus minus psi A minus psi B to be smaller than 0. So this, like those 2 monomials can be 0. Okay, this is good. In other words, we have a limit for this bivector. If we take T go to infinity, we get a constant bivector on this cone times torus. It's quite similar to like a log canonical bracket. The only thing is that now we don't have the full space. We are landing at some special cone times the torus. In summarize, this construction give us from the dual Poisson-Lie group, we get a cone times torus and with a constant Poisson structure on it. This is a so-called partial tropicalization in this example. And we can play this construction to all Poisson, dual Poisson-Lie groups. And actually in the original paper, we're dealing with some more general situation. And now let's just focus on dual Poisson-Lie group. So here is a general construction. Recall that on B minors, we have an open dense set, which is a double Bras-L, GW0 not. So here W0 is the longest element in the world group. And this guy has some cluster structure. And the B star, as I mentioned, it's a subgroup of B minors. So the idea is to use a cluster chart on the double Bras-L as the chart we want to use for K star. So here we just pick any cluster chart. And I will not write down the definition, but here I just give one example for SL3. For SL3, it's a 5-dimensional variety, and we have 5 cluster variable. The blue ones are the principal minors. The red ones are the corner minors. These 4 are frozen variables for the cluster variable, for this cluster. And we have one mutable one, that's this black minor. And so these 2 groups of frozen variables will play some important role in later. And the thing I want to say is that those blue ones, they are principal minors, so they are always real on K star. So this is the chart we choose. Actually, there are a lot of more charts we can choose. For example, twisted cluster charts or factorization charts, and so on. But yeah, I mean, all these are coming from positivity theory or cluster theory. And they provide us a lot of good charts already, and we just use it here. Okay, this is the first step, pick some good chart. Then the second step is to create some cones. So the idea is similar to what we saw in the example. So we consider all possible bracket between .I, .G, and .I, .G bar. And then we write them in the following form. By the following form, I mean, we just pick the .I, .G term and put everything else into FIG, and similar for GIG. And the good thing is that by the bracket, by direct computation, one can see that this pi ig or var pi ig, they're just rational numbers. And this FIG, GIG, they're Laurent polynomials in our variables. Okay, with this, we can play the similar game. We consider the change of variables. As I said, there are some variables, they are just real, so they don't have angles. Some, they have angles. We always scale the, how to say, we always put the parameter t here. And now we can create a cone in this coordinate, in this new coordinate. So here the idea is that because it's a Laurent polynomial, for each monomial in this polynomial, if we want this term to vanish, we get a cone. And there are a lot of FIGs and GIGs. We take all the Laurent monomials and send them to 0.
Yanpeng?
Yeah.
Sorry, I don't know whether I'm allowed to ask questions, but I have a question.
Yes.
So how is it? I thought this Kogan-Zelevinsky is telling us that those FIJs, they're all 0, or is it?
Oh, that's for G, but here I'm considering K.
Oh, yeah.
Sorry.
But isn't it still true that, I don't know, like just.
Oh, you mean, yes, 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 these FIJs, they are 0, yes.
Oh, okay,
yes.
But because you said there are many FIJs and many GIJs, but there is only one.
Actually,
FIJ
there are only GIJs,
0.
yeah.
Sorry.
Yeah, yes, you're true, yeah. Yeah, just I want, yeah, because yeah. So yeah, I should change this, yeah. So as Anton said, actually the bracket for K star somehow part of the bracket is coming from the bracket of G, and that's why the bracket between delta and delta G, they're just a zero. But this guy, they're not. This GIGs, they're not. And then we can create a cone by asking all the monomial terms in this GIGs to vanish. That's the intersection of all like for each monomial you get a cone, and then we take the intersection of all these cones. Okay, so by design we get a limit for this scaled Poisson bivector, which is constant on this cone times the right dimension of torus. Yeah, this is roughly our partial tropicalization functor. So for each dual Poisson-Lie group, we create a set of cones times torus, and on it we have a constant Poisson bivector. And we have a lot of good choice, a lot of good coordinates, theta, and by design, or like by the design of the functor, all these charts, all this cone times torus can be connected by piecewise linear maps and how to say group homomorphism on the cone part, on the torus part, such that they are Poisson isomorphism. And in that paper, we are using in the original paper, we are using some different techniques called potential, but here, because I will not talk that much, so I'm trying to do it down to earth, just for this example. Okay, so any questions so far about this construction? If not, let's.
Yeah. Again, I don't know. I'm probably not allowed to ask those questions. Chen Chang, you stop me.
Sure. I don't stop you now.
Oh, okay, but not now, right? So, but I think maybe one natural question is: it's not obvious that this cone is non-empty, right?
Yes, sure. This cone might be empty. Yeah.
But right, it somehow miraculously turns out it's non-empty.
Yeah, it's yeah, that's why we have a theorem saying that it's not empty. Yeah. So far it might be empty, yes.
Dimar's question, in which sense this construction is a tropicalization? Is it like a limit?
Yes. So actually by tropicalization here, sorry, my computer doesn't want to. Oh, okay. So sorry. So actually, in this part, because for tropicalization, there's one, how to say, there's you can think it's a formal rule, or there is like a limiting explanation, and this changing of variable, you can think it's a mimic of the tropicalization. And that's why we call it partial tropicalization, because we have angles here.
Right. Somehow, then taking this log you made like multiplication into addition.
Yeah, exactly. Because by doing this changing of variable, you basically get the formal rule. Yeah.
And what is the dimension m? What is r?
Oh, sorry. The R is the rank of the group. The M is the dimension or the length of the longest word. So R plus M will be the dimension of the, how to say, of the variety of K star. Yeah. Not really like yes. Sorry. Yeah. like half of the, not really half of the dimension, because K star as a real group is R plus 2m. Yeah, and this R, because the diagonal should be real and the other part can be complex. Yeah, that's why we have less torus. We have slightly less torus. And this cone is R bigger than the dimension of the torus. And together, yeah, you get the full dimension of K star.
And is it also A and N minuses also have these dimensions?
Yeah. That's A. The real dimension of A is R. The dimension of N minus is 2m.
Okay, thanks.
Yeah, as Anton said, this cone, so far this cone can be empty, and also this constant Poisson structure of Poisson manifold has nothing to do with this K star. By nothing to do, I mean like Poisson isomorphism or like anything related to Poisson geometry. So yeah, our theorem will answer this question somehow in some way. So let me drop the theta dependence just to keep the equation simpler. The first thing is that we have two linear maps from this cone to the interior of positive well chamber, such that following things hold. The first thing is that there is a unique point in this closure of the cone, such that the image, for each point in the interior of the positive well chamber, there is a unique point in the cone, such that under these two linear maps, they goes to psi. Yeah, this might sound a bit strange, but if we think about, because later I will say that this guy will have some representation meaning, and if we think about the highest, the representation of a Lie group G or a Lie group G, and they are all parameterized by weight lambda. And for each representation, there is a unique element, unique vector, such that the weight of that guy is the weight of the weight of your module. So basically, this P and P prime plays the role of weight and highest weight in representation theory. Another thing is that the inverse of the P minus psi is a polytope, and all symplectic leaves of pi infinity is given by this P psi, which is a polytope times the torus. The second thing is that the volume of this symplectic leaf equals to the volume of a coadjoint orbit passing to the same psi. Yeah, the appearance of coadjoint orbit here might be a bit strange. Actually, here a good formula should be the dressing orbit of K star, like the symplectic leaf of K star. But since I didn't see what's dressing orbit, and also there's some complication to explain like which leaf it corresponds, so I simply put coadjoint orbit, and I will explain this in the next section. So by this by this theorem, we can see that the cone must be non-empty, and it has a good symplectic meaning or Poisson geometry meaning. It's related to our K star in some way. And this will be more clear in next part. And now let's focus on the representation part, the relation with Langlands dual. And using this data, I want to create a cone. I want to create a lattice in this cone C. And let's do it for our example. Recall that we have a cone for the SU SL2 example. And this cone is this part. Is this cone contains the positive part of psi b. And these two maps are given by this. So psi a, psi b, they are numbers, and alpha is a root of SL2 or SL2C or SU2C. And the P prime is given by this. So they are both something in the positive wave chamber. And we take, and then we choose a lattice lambda 0 on this subset where the P and P prime coincide, such that under this P map, this lambda 0 coincide with the COVID lattice of the positive wave chamber. And in this example, they are just the red point here. And the length, the coordinate of the first point is given by 1/2, 1/2. And next, we want to use our constant Poisson bracket to get a lattice on each symplectic leaf. So first, we identify the polytope, identify the tangent space at each red point with the polytope itself. And then this constant bracket, we use this guy as a pairing to get a dual lattice of the co-character lattice of S1 with S1M in general. So in this example, this will give us all these black points together with these red points. Yeah, if you are familiar with representation theory, you might recognize something already. So each level, it's the the crystal for SL2 for SL2 representation. So in general, we can get the so-called Bohr-Sommerfeld lattice in the closure of the cone. And our theorem said that this cone, together with the lattice, coincides with the so-called Berenstein-Kazhdan cone, together with its lattice for the Langlands dual group of G. So I will not explain what's this cone, but saying something, what's the usage of this cone. So first, by coincide, I mean, so one should first identify their ambient space. Actually, they live on different spaces. To do this, we use the dual cluster variety thing, and the Kashiwara, and this cone, this BK cone, it is a Kashiwara crystal, which means it carries a lot more structures. For example, the Kashiwara operator. And this guy parameterizes the canonical basis of UQG. And actually, we have a question, which is quite important, because this theorem somehow relates Poisson. It uses Poisson geometry to realize this parametrization, but more importantly, how to realize the crystal operator just in Poisson setting. This is our question, and maybe the next step for this project. Any questions so far about this theorem? Okay. If not, I will move to the second part, to use this construction to build action angle variables for coadjoint orbits. So here I just illustrate one example to use more pictures. So by using the Kaling form, one can identify SU2 star with a set of 2x2 triceless skew Hermitian matrices. And the two matrices are in the same orbit if and only if they have the same determinant. And which, if we draw the orbit in cylinder coordinates, we get this sphere. And the whole space is this cylinder, is the ambient space, and each leaf is a sphere. Okay, So before I introduce more notation, let me state our main theorem first. So for each delta, because we have a polytope times some torus, so I want to shrink a little bit of the polytope to get a smaller polytope. I denoted by peak psi delta. So our theorem says that there exists a symplectic embedding from this smaller domain into the corresponding coadjoint orbit. Because in the previous section, I said that this peak psi and oak psi, they have the same volume. And this thing says that actually I can shrink this tropical symplectic leaf a little bit and embed it into the coadjoint orbit. And moreover, for each epsilon bigger than 0, there exists a delta bigger than 0 such that this guy, this p psi delta, has almost all the volume of coadjoint orbit, which means this is an almost global action angle coordinates, but we cannot extend this map to be an isomorphism. So about building action and global action angle global action angle coordinates for coadjoint orbits. There are already a lot of works. It is in the originally it is the so-called Gelfand-Tetting integral systems by Gromov and Sternberg. Their construction holds only for type A, B, D. And later, people are using new techniques, the toric degeneration, to build action angle coordinates for for rational coadjoint orbits in general. And in the recent work of Jeremy and Ben, they upgrade the toric degeneration technique and get some generalized Gelfand-Tetting. And in their work, they showed like for all regular coadjoint orbit, there exist global action angle coordinates. Yeah, from this viewpoint, our construction here is not that useful. Yeah, but the method here, we believe it has its own, value. Okay, now let me try to explain why the appearance of coadjoint orbit and how we build this symplectic embedding. So the key to connect little k star and the capital K star is a so-called Ginzburg-Weinstein map. They show that actually these two spaces, they are different, they are global diffeomorphic to each other. So the difficulty of us to use this theorem is that this map is not unique and there is no canonical way to write down a formula. And also there's no canonical Ginzburg-Weinstein map. So in our setting, we want to consider the scaled Ginzburg-Weinstein map. And the only example we can write down is for SU2. A is a Hermitian 2x2 Hermitian matrices. And in this case, the Ginzburg-Weinstein map is given by this formula. And if we combine this scaled Ginzburg-Weinstein map together with partial tropicalization we built in the previous section, we get the following map. So here, the first part is just the Ginzburg-Weinstein. The second is we take the cluster chart and then apply the change of variable, like taking exponential t psi I and phi something. And then we push forward this t pi k star to this space. We get a t-dependent Poisson bivector here. And on this space, now we have two Poisson manifold. One is just this cone times torus with this Poisson Poisson structure, and the other one is the one we get from partial tropicalization. And now we want to compare these two Poisson spaces. Still, let's look at the example. So here, that's one symplectic Li for little k star. And this is a symplectic Li. This blue part times 1, that's a symplectic Li for the partial tropicalization of k star, capital K star. And okay, now I just write down the image of this part, of this red part, under the map ft, because this map, because we have the explicit formula for in this 2x2 case, and the image is this red part. And now I take a small neighborhood of this blue part, that's the shaded, the green area. So this now the idea is we want to compare the intersection of the red thing with the green part together with this blue part. We want to compare these two things. Sorry, there should be no I for this guy. Yeah, and to construct the how to say, the symplectic embedding is roughly as follows. So first, we need to identify these two spaces. One is this red part, and the other is this blue part. First, we want to identify these two spaces. And after this identification, one can show that those two symplectic structures, they differ by a small term, and also the difference is exact. And with this, one can construct a Moser flow to get from omega infinity to omega t, which is the symplectic embedding we want. Well, of course, like what we want is global action angle coordinates, not just symplectic embedding. So we have a conjecture about this. We hope like the composition of all these maps should have a limit on open dense part on K star. And also this limiting map should be a Poisson diffeomorphism. And this conjecture is true for the SUN case. And also this F infinity recovers the well-known Galfond-Tetting system. As an easy application, one can get a lower bound of the Gromov weights, which I will not explain too much. So yeah, so by this we solve the we give the by combining with the results by Cavides and Castro, we get the equality for the Gromov weights. And that's all I want to say today. Thank you.
Well, thank you, Yanpeng. It's a bit faster. Oh, and but are there questions? Comments?
Yeah. Maybe I have a short comment. Since Yanpeng called the talk on tropical Poisson-Lie theory, Yanpeng, maybe you should say a little bit that there is a hope of having some kind of tropical Poisson-Lie groups, right? And what are the perspectives? What are the obstacles? Or what's your view?
Oh yeah, so yeah, actually this I discussed this with Anton like roughly a year ago. There we want to have a tropical Poisson-Lie group, which is which is a cone together, which is a cone times torus together with a constant Poisson structure. So we know one of the important thing in Poisson-Lie theory is the dual between K and K star, and also the action of K on K star, the so-called dressing action. And or at least my goal recently is try to somehow tropicalize this action. And the idea is this action should be some continuous crystal on this guy, and especially in this K star case, it should recover the Kashmir operator on this BK cone. And also one thing is that why this action is important is that we want to have some reduction thing, because in Poisson geometry or symplectic geometry, the reduction procedure is quite important. And one of the examples, if we have several copies of coadjoint orbits and we want to do reduction for this, and the key, also the difficulty here is to have a correct action of the operators, I think. I don't know if this.
So Yang, maybe I hope so.
Yeah.
So it seems like you go from the semi-classical word to the tropical word. There is some, you find something, right? You find you located something in this new tropical word. So what is that thing you find over there? Some operators, some already existing, or it must be an aim. You go there, right?
Yeah. So actually, like one of the motivation of this is actually to construct the global action angle coordinates for little k star, and but from the result viewpoint, this is done by Ben and Jeremy. So but I think our method still have its own value. I think at this moment, I don't know, I cannot say too much.
Or maybe it's because the dualization. You see it more clearly in the tropical picture, or?
So sorry, what is more clear in?
Well, I also just have the impression. So yeah, I try to understand the thing again. Is it because taking the dual, this thing is Poisson and Poisson dual? This thing you see more clearly in the tropical world?
As this. Well, I think now, no, because there's no tropicalization of the compact group K. And yeah, so we can only see the tropicalization of K star at this moment.
Yanpeng, may I comment?
Yeah, sure.
Yeah, no, I think at least what I see, there are two things. Without this tropicalization, probably it's not so easy to see the relation between Poisson-Lie duality and Langlands duality.
That's probably
which is quite surprising and interesting, and I don't think it's well understood. So what Yanpeng was explaining and what we were doing with it, it's a kind of observation, right? So it matches very precisely some objects, which is very nice, some lattices which are created. I think on the Langlands dual side, it's a canonical construction. On our side, we need to make some very mild choices, but still after that, it's quite surprising that those objects match. But I guess there should be some kind of more conceptual explanation. Maybe I don't know. One can imagine maybe one should use infinite dimensional Lie algebras and Lie groups to pass from one to the other. Something, right? There should be some better way to relate, like our theorem on the relation between Langlands and Poisson-Lie duality. It should have some more conceptual source, which would probably bring some beautiful picture in. So that's maybe one thing. And the other thing is those story of Ginzburg-Weinstein maps. So Ginzburg-Weinstein maps are very, very interesting maps. So there are many constructions on the market. They are more or less all implicit, even though they are beautiful. So when we tropicalize, it looks like then it gets some kind of explicit formulas or explicit and simple properties. So that's, of course, that's why I think that's one of the motivations that Yanpeng mentioned, that we want to have the tropical Ginzburg-Weinstein map. And in some cases, we do get it. So the idea is that you have a whole family of Poisson structures in that scaling parameter t. At t equal to 0, you get the KKS bracket. At t non-zero, you are getting some kind of Poisson brackets, scaled Poisson brackets on the dual Poisson-Lie group. So the isomorphisms between them, they are kind of usually complicated. You can write them in the SU2K in the rank 1 case, but otherwise not so much. And then when you send t to infinity, all of a sudden it again simplifies. It becomes some kind of object you can work with. So this goal of including t equal to infinity in the family, it's partly achieved and partly not quite achieved. It would tell us something about those Ginzburg-Weinstein maps and about the Poisson-Lie group. And then you can probably also ask how to quantize all this picture, which would bring in those crystals, so Kashevara crystals that Yanpeng was talking about. At least that would be my perspective on why this tropicalization procedure is kind of useful and interesting. Yeah, Yanpeng, sorry for like stepping in.
No, thanks for the explanation.
Until like when I was a graduate student, Alan stopped in my talk and give such speeches all the time, and that was great.
Oh, but as Yanpeng mentioned, he has already graduated. So.
Yeah.
Oh, yeah. Well, we don't count the COVID years. Oh, thank you very much. That's indeed very nice. And like, are there other questions and comments? So as Anton said, they're like there is like in 15 minutes another talk for people interested in, and we can go. And so I don't know whether it's really polite or not, but thank you for so yeah, I do agree that once you go to there are all these combinatoric picture that probably will make the calculation really fascinating. That would be nice, but could you go back to this Langlands duality and the Lie Poisson duality? Is it how do you observe the similarity? I was actually
yeah, because how to say, like in my talk today, this cone is, we get this cone by doing all the tropicalization of the remaining term of the Poisson bracket. But actually in reality, this cone is, we get this cone by using some potential. And actually, to get the Langlands, to get the BK cone, they are using the same potential. And that's why, like, we observe that there might be some connection
between,
even on the lattice level. Yeah.
we may observe more later. No?
I think I have one more small comment. Yeah, Yanpeng, if you can go to this equality of volumes.
Sure. Yeah, here.
Yeah, in fact, I think here there is a nice question. You know, this volume on the left, this this beautiful peak psi is a product of a polytope and the torus. So in fact, the volume of this space is simply the Lebesgue volume of the polytope times 2 pi to some power. So the volume of the coadjoint orbit is simply known. It's there is a Weyl formula, which is the semi-classical limit of the Weyl character formula. So there is an explicit formula. Now, at the moment, the proof of this statement is using very heavy tools from representations theory. And it's kind of very, like, it's probably, it looks too complicated for the statement. So the polytope, the Poisson structure on the polytope is known explicitly. So the question is, can one do some kind of easy combinatorial proof of this formula? I think that's an interesting question, which wouldn't refer to representations theory. Just to compute the volume of that polytope, maybe by localization, right? By doing something like extracting some information about vertices of it. In principle, this is not supposed to be some extraordinarily difficult fact. At least I believe. But at the moment, how it's done in our joint works with Yanpeng and Benjamin and Jeremy, or with Berenstein, it's very, very involved. That it should not be involved, I think. But I mean, I think that's a very interesting open problem, which is not using most of the theory that Yanpeng was talking about today. It's only using some whatever combinatorics of polytopes, some kind of Cartan metrics of our Lie algebra, and the Weyl formula for the volume of the orbit. I don't know, Yanpeng, whether you would agree.
Yeah.
Okay.
Because the result involves data which does not touch all complicated theory.
Sure. Yeah. That's I mean, yes. It is like in principle, it's supposed to be a simple fact, but now it's a simple fact with a complicated proof, which is probably calling for someone, maybe us, maybe you people, someone to make it better. Like this, this should not be complicated.
Yeah.
It should be beautiful and nice and so on. But I mean, and the answer, as you see, it's very nice. So, yeah, please do it.
Yeah. If people cannot find, then this thing is a deep result, like a Fermat last, which could be understood easily, but you need to do a lot of deep theory. Okay, so thank you very much for Yanpeng for your talk, and thanks Anton for wonderful comments. We've got like 2 talks. That's very good. And so I maybe I encourage people to go to the next talk, and we see each other next Thursday.
Bye.
Bye.
Thank you.
Bye.
Thank you. See you next week.
next week.
Bye bye.
See you.